I'm Kade Bowers,
And I'm Matilde Garcia.
and this is Lab 9 Michelson Applications.
We set up the Michelson interferometer so that we could measure the wavelength of different sources. To do this, we first need to calibrate our equation for our setup, and to do this we use a helium neon laser with a known wavelength of 632.8 nanometers. We used this known wavelength and plugged it in into our calibration factor equation. We also counted 100 fringes as we measured how much the optical path distance moved. And then this gave us a calibration factor of 1,900,000 nanometers per inch.
Using our calibration factor, we counted out 50 fringes using the mercury source. This gave us a wavelength of 549.2 nanometers, which is accurate within 0.59% from the actual value of 546 nanometers. If we miscounted by one fringe, that changes our answer by 11 nanometers. And if we want to know the wavelength within 0.1 nanometers, we need to count 741 fringes.
Oh, I see what you're saying. Okay, yeah.
For the sodium source, we found out that the wavelength was 589.6 nanometers, and this is within a 1% error of the actual value of the wavelength, that is 589 nanometers. As the fringes become darker and clearer, it becomes easier to count the number of fringes that pass, and as we move over a large range of optical path differences, we see the source oscillate between crisp and blurry fringes. Using the wavelength we measure for the sodium source, we calculated the spectral line separation of the sodium doublet by measuring the difference between the blurry fringes, and we plugged it into this equation. We also use our calibration factor. We found the spectral line separation to be of 0.521 nanometers with an error of 13.1% with respect to the actual spectral line separation of 0.6 nanometers.
For this section, we measured the index of refraction of air. Doing that, we replaced the corrector plate with the vacuum chamber, and then we pressurized it to 55 centimeters of mercury, and then we slowly released the pressure and counted 20 fringes. We found a change in pressure of 46 centimeters of mercury. Using the change in pressure and the change in the optical path difference, we could calculate the slope of the line of index of refraction of air versus pressure. We found a slope of 3.08 times 10 to the negative 6 inverse centimeters of mercury. To find this plot, we centralized at 76 centimeters of mercury, which is sea level. Tucson is at 79.6 centimeters of mercury, which gives it an approximate index of refraction of 1.0032.